charts for matching, and I'll go through a couple examples. Then we're going to get into S parameters. When we get done with that, take your questions. And one other reminder, I think I said everybody this, but it was, we talked about it in class. That project is due on Friday in class, so make sure you send me the email with it. Now, everybody has to demonstrate their code in my office, so you can do it. You're doing it today. There's people who are doing it today, but it needs to be demonstrated in my office, and then handed in on Friday the actual code. Send me, or I'll put it on ABIT, or I'll put a Dropbox thing with the ABIT project on Canvas, so you can put it in there with figures and your write-up. Okay, go ahead.
I don't have MATLAB on my computer.
Well, just use the one in here, but you need to do it.
Well, I'm saying how would I'm going to show you it.
Well, you just send me the code and I'll run it. I'll be happy to run it.
So we need to email you the report.
No, you're going to put it on ABIT, the report and the code, in the folder that I put on Canvas.
Yeah.
It's not there yet, but it will be after class. Can you remind me, Cole?
As a PDF?
Well, you're going to put the code in a MATLAB script format, and you can embed it in your PDF of the actual of the report. The thing you do with the figures and discussion.
Can I just copy and paste the code into the PDF?
You all know how to save a MATLAB file, don't you? A .m file. Save it and just take that and load that again, the MATLAB file with that. I mean, if you want to, you can put it in a Word document or something and upload it, but the .m files should be fine. Okay? All right. Now, and I will put that up there right after class, I guarantee you. And if you have questions, see me. But remember, everybody has to demonstrate, because I've had people literally send me garbage, wouldn't run, and what do? Give them a D, and I don't want that. I want to make sure it runs, make sure the code is there, what you've done, the problem statement, discussion, how you solve the flow chart, and then discussion. I just want to get this done. We've had to do stuff like this, I'm sure, in other places. So today, what I'm going to do, I gave you some problems, right? Y'all with me on this? Okay. So this is the impedance matching using the rotated Smith chart, and we will, what I wanted to do is start by an example. Let's do 1013, and we'll do a couple. I'm going to do examples where you're going to do it when the normalized load is in the rotated Smith chart, inside the circle, R equals 1 circle, outside of it, then outside of both, and hopefully we'll be done. So this is problem, it's 1013, correct? Right?
Yeah.
Those are a bunch of, they were straightforward problems, but you do need to print out some of those solutions. I'm telling you this. So I start by saying the problem defines a characteristic impedance Z naught of, is it 50 or 100? 50. 50 ohms. Then over here you have a load, and the load is what?
10 plus J15.
Okay. Unfortunately, what's the one above it? I'm looking for a load. When I normalize it, it'll be inside the 1 circle.
1014 will do that.
All right, let's do 1014, Will, you sure?
Yeah.
All right, give me the load.
80 minus J50.
Yeah, that'll do. Is it 50 over here?
Yes.
And what we want is an L section network. So it could either be series parallel, or it could be series parallel that way. You all with me? Those are your options. So for this thing, the way we do it always, there's a Smith chart. I'm going to eyeball this one. And this is the rotated circle right here. So the steps, first step is always getting ZL, which is going to be Z capital ZL over Z naught. In my case, ZL is going to be 80 minus J 50 over 50. So this is going to be 1.6 minus J1. You all agree with that? Now please make sure you know how to find this. This is the problem that if you don't understand these problems and you mess up on a final, it's, you know, you're going to get 6 problems basically. You mess one up, you're hurting yourself. Don't know how to do these problems. You're going to get one. So I got to plot that. Now, the real part is 1.6. So the trajectory of 1.6 on a Smith chart is about here, if you look at this. This would be 1.6 is the real. Can everybody find that? I hope you have Smith charts here. Did you all have them? Pull out your rotated Smith chart, make sure you can do this. You need to have these things. You need to make sure you stay up with this because you don't want, really, you don't want to have to get a lot of cramming. I mean, you're going to cram anyway, some of you, but you want to try to just let this stuff sink in as we go through it. The less cramming you do, the better you perform in general, in my opinion. Now, the minus J1 is where? Well, here's minus J1. You all agree with that location? It's the South Pole, right? The trajectory of this, and I'll do it with blue if I can, looks like this. Can everybody follow me on that? That's the minus J1 trajectory. It is a circle, but the center is way out here. So the intersecting point is right here. And this would be 1.6 minus J1. And that you would always label 1. Sometimes people don't label their points, they lose points for that. You have to tell me where you went in. That's the first point. Now, this one is clearly inside the R equal 1 circle. Everybody, get in. So no matter what imaginary component I add to this, I can only move around this trajectory. I can't get to this point. That's the point of what I'm doing. You with me? So I have to go to the admittance domain. So I take 1 over this. This is ZL. And the admittance domain is going to have a point right here. This length will be that length that goes right through the center, and this is YL, which is 1 over ZL. Can you give me that value, anybody? If you have calculators, just take 1 over, or 1.6 minus J1, and give me the real and imaginary part. Look, if you work with me on this one, it'll help you. When you see how to do this stuff, if you have a calculator, and do it, it really is helpful. It's the more often you see this process, the more likely you are to remember it. What are you going to do?
0.45 plus J 0.28.
So YL is 0.45 plus J 0.1?
28.
Okay. And we are in the admittance domain and it's normalized. You all with me? Admittances are in parallel. So the next thing I'm going to add right after here is going to be a parallel leg with a Y value. Everybody with me? Now the question is, how much am I going to add? It will always be an imaginary number, never a real number. You with me? A real number is resistance or admittance. So if you look at this, I have 2 possible choices. Please hear me on this one. I'm going to try to be clear as I can be. There is a trajectory, and the real part is 0.45. So if you look at a circle out here, R equals 0.45. That is the circle we can move across. As we add more positive J, we move this way. Can you all follow me? Everybody with me on that? As more negative J, we move this way. Now, here's where you have to think. Remember, we're going to be adding an admittance, but that is a normalized admittance, all right? Now, I want you to just hear me on this. If we have a capacitor, the actual impedance of the capacitor right here would be 1 over J omega C, or minus J over omega C. That would be the impedance of a capacitor. Do you follow me? the normalized impedance of a capacitor let me do it with purple. This is the impedance. The Z normalized of the capacitor is going to be simply minus J, and it's going to be, or really I'll just put it this way, it's going to be 1 over J omega C Z naught. You all agree with that for impedance? The normalized admittance, which we're up to, the normalized admittance, Yn for this capacitor, is 1 over Zn, and that's going to be J omega C Z naught. Now you see it's adding a positive J. Does everybody follow me on this, class? So if we want to add something in parallel that's a capacitor, and we're in the admittance domain, we would, we're going to be adding a plus J value. If I went from here to here, this would be a capacitor. I'm just putting that symbol there. Y'all with me? If it's an admittance, y'all with me? That would be a normalized admittance, and that would be the amount. I'm going to tell you how you actually calculate this amount. Here we have a value, and Keenan or somebody with a good Smith chart, I need you to help. This value is 0.45 right there, plus J.28. Where does this trajectory intersect the rotated one circle? This would be 0.2.
1 minus J.
Wait, no, right here.
Right.
Keenan,
Look at the wrong point.
you see it right here?
Like J 0.5,
Pardon me?
0.5.
J.
So it's 0.45 plus J 0.5? Just confirm.
J. The imaginary component is J is 0.5.
Right here. So this is the third point right here. And this point has a value of admittance. So we went from 1, 2 to 3. Y equals 0.45 plus J 0.5. Is that correct? Right? You all see it? Now how much did we add? Well, we had, this is 0.28, right?
Yeah.
Correct? We added a value of 0.5 minus 0.28, correct? So what is that value? 0.22. The actual amount of, we're going to have J of 0.28, I'm sorry, 0.5 minus 0.28, right? So that's going to be J of 0.22. You agree with that? That's what you put here. You're going to have this value be J 0.22, and this is, you might as well say, the capacitor. Y'all follow me? Jack, you with me on this one? What don't you understand?
No, I missed where we went from the 0.45 plus J 0.5 to where you're at right now.
This is where we were when we took 1 over ZL, right?
Okay, yeah.
That's 0.45 plus J 0.28, right? Now we need to add something so we can move along this real value of 0.45, that trajectory to get to the edge of that circle. And the amount we add to it is going to be this, J 0.22, according to what I've been told. Do you all agree, class? That's adding a capacitor in parallel. I might add, that is the preferred way to do it. The reason is, if this is actually something that's going to feed like a bipolar transistor, you can't have an inductor here because they can't be DC biased. An inductor would short it out. You always want capacitors in parallel, inductors in series if at all possible. Can you follow me, class? Now, the next thing, now that I'm here, this is my value, and I'll call it Y prime right here. I added this to it. We'll get that capacitance in a second, but it's really straightforward now. This J 0.22 is associated with capacitance in the admittance domain, right? So you know the normalized admittance is J omega C Z naught, right? Can everybody follow me on this? All right, so to calculate the value of this capacitor, if you look at this, I know that J, and this is going to be omega C Z naught has to be equal to J 0.22. Do you agree? Now, I don't know what the frequency is, but if you tell me,
1 gig.
1 gig?
Yeah.
10 to the 9th hertz. So that means the value of C is simply 0.22 over 2 pi times 10 to the 9th. And then it's going to be times Z naught, which is 50 as far as I understand. And can you give me that value? This is a small value capacity.
0.7 picofarads.
Yeah, that is small. Very small. I'm just telling you, when you get sub-picofarad capacitors, the lead length can change it significantly. You have to be real careful with this stuff. So that's the capacitor we use if we're going to add a capacitor in parallel. Now we're here. That's our third point. Where do we go next?
Admittance. Or
We're at the admittance. We're
Impedance.
going to go to the impedance domain, right? We're going to take 1 over that admittance. So this impedance here, I'll call it Z prime, is going to be 1 over my, what I'm calling Y prime. And what is that value? 0.45 plus J, 0.5 1 over that. It better have almost 1 on the first part.
It's 0.99.
Okay, we'll call it 1. Minus
J 1.1.
1.1. All right, now we're going to add something in series. Whenever you add impedances, they're always in series. Admittances always in parallel. You follow the idea?
Real quick, if you're on the one circle over here, how would you get a value other than 1 as your real part?
You can. It's 1. It's 1, but we got to get rid of the imaginaries so we have the normalized value is just 1. When I multiply that by Z naught, now I've got Z naught I'm looking into. That's what I want. There's no reflection.
All right, that's what I was assuming. How would you get like 0.99?
Because when he did, it's rounding.
Oh, okay. I see.
See, you know, we're doing something where we're using a graphical solution. It's not a mathematically exact solution. You go 0.99, it's pretty darn close to it.
I forgot he calculated it instead of just like looking
Y'all with me?
at it.
You guys with me over here? Follow me? Okay, I'm trying to read faces. I'm not good at that, I found. Okay, I got that. Now, what I need to do is get rid of this minus J1, but it's in the impedance domain, right? I have to add something to get rid of it. Y'all follow me? How much do I need to add? Plus J1.1, right? Y'all follow me? So if I look here, that's the capacitor. My inductor right here, and I'll show you in series so you know. And L here has a reactance of J omega L. So the impedance of the inductor here would be J omega L, right? I'm just showing you the obvious, correct? The normalized, when you say normalized, it means divided by the characteristic impedance. That's all it means. The normalized value is going to be J omega L over Z naught. You all follow me? Now remember, you start in the impedance domain to do the normalizations. You'll get yourself confused if you start thinking about, well, I'll normalize it in the Y domain. What do I do with that Z naught? Do I divide or multiply by 1? Don't do that. Just work in the impedance domain for starters, okay? That's normalized, right? I'm in the impedance domain. I want it to be impedance. We want this value right here to be J1.1, right? So this element here is going to have a value of J1.1. So when it's added, it'll annihilate the minus J1.1. Now I can say J1.1 equals J omega L over Z naught. Now, do you all follow the reasoning behind that? Now you can calculate L. L is going to be what? It's 1.1 times Z naught, right? Over omega, or 2 pi. I'll just put it in 2 pi times 10 to the 9th. Well, what do you get for L? Anyone?
8.75 nanohenry.
Is that the right answer? Thank you. Now that's the way you do it if you wanted to start and add a parallel capacitor. Are you with me? I don't know if he does this other solution. It's not the preferred solution. I will probably tell you I want the capacitor in parallel so it will pass DC, or I'll say I want this thing to allow a DC bias, and the inductor will be in series. Do you all hear me? Now there's some cases you can't do that, but for almost everything you can. Now if I went this way, right, let me tell you, this point will be same real part, opposite imaginary part. So this part here, I'll call it y double prime, would be 0.45 minus j 0.5. Do you all follow me on this? Now, if we wanted to go this route, this would be an inductor. Y'all with me? I want to make sure you see the reasoning. Y'all follow me on this? Well, how much imaginary part do I need to add? Well, this has got minus j 0.5, and it started at plus j 0.28, right? Do y'all see you would add a minus j 0.28 plus 0.5 or minus j 0.78? Look, if you're here, how much do you guys subtract to get here? That's point j 0.28. How much do you have to subtract to get to minus 0.5? Minus 0.28 plus quantity, minus 0.28 plus 0.5. Y'all with me in class? So it means what I have to do is add something. If I was to do it with an inductor in parallel, I'm just going to show you this, which is not the preferred way. If that's the ZL, then the inductor here would have to have an actual normalized value with everything considered of, in the admittance domain, of minus j, and it would be 0.78. Y'all with me? Can you follow the trend? Now the actual value of the inductor there would be what? Now I didn't put this over here. So that's the normalized impedance, right? Everybody? What's the normalized admittance?
Z naught over j, negative
Just
j.
flip it, right? So it's minus j, right? Minus j z naught. I don't know if he does this for this one, over omega L, right? So to calculate this value of L, I can say that minus j 0.78 has to be equal to, and if you look at that over there, it's going to be z naught minus j z naught over omega L, correct? First, do y'all see what I'm doing here? I want to make sure. You guys with me? All right, get rid of the minus j. Matter of fact, I'm going to get rid of it. I get this, right? We want to solve for L. What is L? It's going to be z naught, right, over omega times 0.78. And that's 50, right? Can somebody calculate this? So it's 50 over 2 pi times 10 to the 9th times 0.78. And give me that value, because I can't do that in my head. Now this would be an inductor in parallel, which is not the preferred way. But I'm just showing.
10.2 nanometers.
Anybody confirm that?
Yeah.
Okay. Y'all with me? Want to make sure you see it? Greg? How many we got here? 2, 4, 6, 8, 10, 11. No, Brad. We're missing a bunch, aren't we? Okay. Maybe they got it down. Now, if I do that and I move to here, what's my next step? That's what? The admittance, what did it say?
Get your normalized impedance.
I have to take 1 over this to, what?
Why couldn't you just go from the bottom part where you just were, that, and just go up to the middle, like this curve?
Because this is the trajectory of the real part you have to follow.
You have to follow.
You're
the
only
trajectory.
adding imaginary values.
Okay.
You can only follow, I call it this orbit, or trajectory. You can't get to the middle just in the admittance domain that way. you have to go now to the impedance domain, which is taking this taking this one over that, it's gonna be over here, right?
Yeah.
What's the value gonna be? It's gonna be exactly this, only it'd be 1.6 plus J1. It'd be a conjugate point. So this one's gonna be 1.6 plus J1, correct? So now, I have to add something that will, in the impedance domain, get rid of that plus J1, which is a
Capacitor.
capacitor, because capacitor have a minus J sense of impedance. Y'all follow me in this? Can y'all follow me? So I know if I'm showing you the opposite solution, I'm gonna have a capacitor here. Now the normalized impedance of that thing, after all is said and done, has gotta be minus J1. That's an impedance though. So this has to have a minus J1 sense. And now when the actual capacitor, if I want to calculate it, how do I do it? Well, this is an impedance, right? So I know normalized it's minus J1 is equal to, what's the impedance of a capacitor? 1 over J omega C, right? Or minus J over omega C. And to normalize it, we Z naught, right? This is impedance, right? Divide by Z naught, right? So we can see what? Get rid of the minus, get rid of the J, right? I can see that C is going to be what? 1 over omega Z naught. Do you agree with that? What's the value of C here? I don't know.
It'd be, what happened to the 1.6 on the left side? Or you had to subtract.
Was it?
Wait,
Oh, I'm sorry. Wait. No, hold on.
Yeah,
No,
you got your numbers.
this isn't 1.6, it's 1. Sorry. This, hold it. It's 1 minus J 1.1. Sorry. This is 1 minus J 1.1. It's on the rim.
Plus.
This should be the value. That was my bad. It should. This value is right here. That has to have a real part of 1.
Yeah,
Right?
Uh-huh.
I'm sorry.
and so that would be the real value of 1 plus J 1.1.
This is 1 minus J 1.1 was the first solution.
And then the conjugate.
Is going to be 1 plus J.1. My bad. Now you have to add minus J1.1, and I'm sorry if I messed that up. So this value here is minus J1.1, correct, class? I'm sorry about that. You all see the mistake I made? Everybody okay? So what's the value going to be? Well, now I'm going to do it right. This is actually going to be what? This is going to be J1 or minus J1.1 because that's the value I have to add. This is just minus J. So C would be equal to 1 over omega Z naught times 1.1, correct? What is the value of C? I don't know.
2.89 picofarad.
All right. Those are the possible solutions for an L network. If the load was inside the one circle, there's both solutions. You with me? Did he give you both or just one? All right.
I think he solved, he didn't do it this way though. If he did, I think he provided some other solution, but it didn't even.
This has to be the way he does. It can't be anything but that.
I'm just saying he didn't show it on the Smith chart the way he did it.
Well, that's essentially what he did. And the values, are they the same as this? Okay. Now, that's if it's inside the one circle, the impedance circle, right? Now we're going to do one where it's inside the rotated circle. You with me, class? I want to make sure everybody's with me. All right, now follow me on this. If you didn't have a chance to really delve into this, please be attentive here. People get very confused on final exams. They get confused on all exams, but the final especially. And we've been keeping up, a lot of this won't be a problem at least. Now, is this final, is it 1 o'clock on Wednesday?
Yes.
Pardon me?
I think it is.
One's at 8, and I think that's my 3800.
Yeah, that one's in the.
And then there's one in the afternoon. I'm gonna try to get all the grading done on Wednesday if possible.
All of it?
No, because I'll have the projects graded this weekend. I'm gonna grade all the projects, so that's it for the projects. Then when the exam's done, the final exam on my 3,800, there's not that many students, I'll grade it before this exam. After this exam's done, I'll grade that. Then I'll have your grades calculated and hopefully up, I hope, by first Thursday. When you come in Thursday, you can see them. But at the latest, it'll be Thursday late, whatever it is, 5 o'clock, the roll time. And it's just if I have to double check something. Okay. I'm trying to get this stuff out of the way quick. Because you're gonna have, what's the last day of finals?
Thursday.
Graduation Saturday, right? Is it? I mean, I
We're probably not graduating in this class.
well, there's problems, but you know, the funny thing is, you can never be sure. We're missing people. I have had people that were planning to graduate in my summer courses that are junior level. They needed that. And some don't. I hate to say that. It's like,
More turtle run into the water.
I mean, honestly, people sometimes think, you know, it's just, they're going to pass. It's my last semester. They're not going to pass unless you pass. And this is a horrible fact. I hate to see that with people. All right, back to this thing. Now, let's do problem 1013, the original problem I was going to do. For this one, I was trying. If you were, I am right now, trying to encourage a class or getting people to perform better is one of the hardest things in the world. I don't want to criticize, that's the worst thing. You want to encourage them, but how to encourage is a tricky thing. All right, so for this one, still characteristic impedance of 50, is that right?
Yes.
50 ohms. We got a load over here, as I recall it. What was it?
10 plus J15.
That's small, by the way. And now we want an L-section network, just as before, to connect these two. And the reason we want L-section, not any kind of a stub, is because real estate is expensive. Any length of line takes up a lot of space on this Doroid board, and it is expensive. Let me see what we can do here. All right, and here's my rotated Smith chart. If you have this, let me draw a little bit. Please get them out, and if you can, mark them. You don't want to be the guy that just lackadaisically doesn't do this until the last minute. You're hurting yourself. You know, the cardinal rule in life, don't hurt yourself. Okay, I'm trying to draw a Smith chart, give you an idea what's going on. Okay, now for this one, what do we always do first? One is what? Anyone? Normalized impedance, gotta do that. That should be just a knee-jerk reaction. So ZL here is gonna be the load, 10 plus J15 over 50, right? So what is that, 0.2 what? Plus J of?
0.3.
Does everybody agree with that? You all understand what I'm doing, right? And you know why I'm doing it. I need that to get into the Smith chart. That's my entry point. I come over here, where is that? Well, that point, I got 0.2. 0.2 is something like this. If you look at this Smith chart, please do. This trajectory has a value of 0.2. You should be able to find that. Take a look. If you have the rotated Smith chart or a regular Smith chart, you should be able to see that. Take a look. Everybody have access to one? Guys? Fan, do you have one? You got a Smith chart or not? Can you find it? 0.2, Greg? Holden? I'm trying to make certain. I know you know it.
Looks like a person with eyes.
Huh?
Looks like a person with eyes.
Kenny.
All right. Stop it. All right. Now, where's the point we're locating? 0.3? Well, 0.3, I'm going to guess is about here. Is that about J 0.3? Look out here. There should be a 0.3. Can you see that? And it's going to be the one that intersects at J 0.3. Can you see that, class?
Yeah.
Where the lines cross is the point. So this point right here would be 0.1, and it would be ZL equals 0.2 plus J 0.3. Does everybody agree with that? Now that's inside the rotated circle. Now I want to make this point clear. Remember, if that's an impedance, anytime we add impedance that's imaginary, and that's the only thing we can do, we can't add real because it would cause loss. Do y'all follow me? So we move along this orbiter trajectory. And you can see no matter what we do, we can't get to the center. So it means we have to go to the other domain. We started an impedance, right? We have to go to the admittance domain. That's ZL, so we come down here and we find out what this point is. And this is YL, that's 0.2, and YL here is going to be 1 over ZL. And what is the value of that, guys?
So you're taking the original point and you're going straight into the admittance.
I have to. I can't. If I add impedance, I can't get to the one. I can't get to the center of the circle, right?
He does it.
Huh?
He adds he does it differently.
Well, look. I'm going to say.
He does it differently.
All right. There's a couple. Hold it. You can do it that way. Let me just say this. This is impedance, right? Now I could add impedance. I get to here, and I could add impedance as I get to here. Those are legitimate things. I guess we'll do it that way. I mean, I'll do it the way he's doing. I'm not going to do this way. So if you want to add impedance, you know, I guess that may be in some ways preferred. There's less steps, but if I go here, I'm going to have to add admittance first, so it's in parallel. That's the only reason I'm doing it. Because an admittance in parallel, I can always choose a cap. I can always do it. So if he's going to add impedance, if I go from here to here, that has to be an inductor.
Yeah.
Are you with me, Clyde? By the way, the good point is, does he have in the statement of the problem, he wants a series inductor parallel capacitor, or he wants to be able to bias for DC? I don't know what he said.
No.
Nothing?
L section matching number.
And that's it? Okay, well, he definitely wants a capacitor parallel. So if I go from here to here, I need the value, if this is 0.1 and this is 0.2, remember the real part never changes. What is the value here? 0.2 plus JY. That's on the rim of this rotated circle.
0.4.
Confirm it, everybody. 0.4? Follow the trajectory. Can you guys see it? Greg, Holden, you guys see it? 0.4. Now, how much did I add? 0.3 to 0.4 is point. So I'm going to add, and this is going to be an inductor first, which is okay. Now, so I'm going to add an inductance with a value of J 0.1 that's normalized. Correct, class? You see this? What is that in terms of the actual inductance? Well, remember, J 0.1, start with the, what is an inductor's inductance? It's J omega L, right? And if it's normalized, you divide by Z naught. And so that means, simply said, when I want L, I get rid of the J's, and L is going to be 0.1 times Z naught over omega. What's the frequency for this one?
1 gig.
Again, it's 1 gigahertz.
I think
Okay,
it's
he likes
2.
to, what's
I
that?
think it was 2 for the other one.
This is 10.13. Is it 1 or 2?
This one,
This one's 1
1
gigahertz.
gig.
What's
The
the
other one was 1 gig.
They're both 1 gig?
Yeah.
There's a 2.45 in there somewhere.
Yeah, he keeps all the Xenon, it's about the same.
50 is good. 50 is typical. Right. Microwave testing, microwave development. Now, you're gonna find out a lot of your transmission lines in the real world, transmission lines are 100 ohms for losses. And the coax cable that comes to your house, I think 75. You're gonna have to check me on that. Okay, so what is this gonna be? 0.1 times 50 over 2 pi times 10 to the 9th, and what do you get?
0.8 nano.
80,
Nanohenries?
I got 80 units.
Check that out. 0.1 times 50 is 5. 5 over 2 pi times 10 to the 9th.
I'm getting something different.
That's 2 times 10 to the 8th times 2 is 4 times 10 to the 8th times pi. That looks like 0.8 nanohenries. Anybody confirm that? Greg, you got a calculator?
Yeah, this is 0.8. Just grab this.
I think it is 0.8. Y'all with me? Is that the answer, by the way? All right. So we got the inductor as 0.8 henries, and I'll put it down here. So now we're right here. That was 0.1. Now we're at this point right here, which is 0.2. Right? So what do we do next? We went from here to here, and now what?
In minutes.
We go to the admittance domain, because we're going to be adding something in parallel. So where are we? We're down here, right? And for this one, what is the admittance? It's going to have a real part of 1 minus j, what is it?
2.
J, 0.2 or 2?
J2.
Okay. You agree? This one I don't like. I don't think. Well, maybe I do. No, I take it back. I do. So what do I need to add to get rid of this minus J2? So I'm going to end up there. That's where I want to end up.
2.
Plus J2, right? So here, I need to add a plus J2, and that's a normalized admittance. It is a capacitor, so this is going to have a value of plus J2, and that's a capacitor. So then we go and we say, I know J2 is equal to, this is the normalized admittance that I erased, which would be J omega C Z naught. First, does everybody remember doing this? This is the normalized admittance of a capacitor. Correct, class? Jack, do you see this? You with me? I want to make sure everybody's with me on this, that I'm not losing. I'm just trying to find these values from the normalized ones. Now, so what is C going to be? Well, C is really going to be 2 over, and you can see this, it's omega Z naught. And that's 50. So I have 2 over 2 pi times 10 to the 9 times 50. Anybody got that?
6.37 picofarad.
I like that better than the 0.7. So this capacitor is 6.37 picofarad. Anybody, do you all confirm that? Now that's an appropriate solution. We don't have to do it the other way, but you can go to the admittance domain from here directly. And then if you're in the admittance domain, you would have to add something, well actually from here to here, you'd be inside there. Then what you're going to have to do is add an admittance to either get here or here. You can always add a capacitor if you figure it out. You know, you always want a plus J would be a capacitor. So from here to here would be plus J. Then you go down here, and then you would add an inductor. You with me, class? That would be a different solution. That's probably a better way to do it. There's less steps.
So the shortest path is always the best.
No, it depends. If you in the admittance domain, plus J. If you're going to add plus J, it's a capacitor. If you're in the impedance domain and you're going to add plus J, it's an inductor. Remember, you always can go 2 points. You can go either adding capacitance or inductance. Which way do you want to go depends on what you want. With me, class? Everybody see this? And that's a classic kind of problem. It's the class of problems. Anything in the rotated circle, when the impedance lands there, you can add impedance until you get to the edge. You might as well do that. And then go to the other one and add admittance to get rid of whatever's left. You with me? Finally, I don't know, does he have one where it's outside both? Which one is it? All right, let's do that one. Now it can be outside of both, and there you're free. You can do this so many different ways. So let me do this one, and then we're going to do S parameters. Now, how many have tests on Friday besides the quizzes in this class? Is that thermo or what? Just thermo? You got another one?
For me, yeah.
All right, now I don't know anything about thermo tests. I hope you guys do well. I'm not going to overwhelm you, but I am going to understand. You understand the last quiz is coming up on Friday, and it does replace any you missed, or it drops your lowest. You all with me? So I would spend time and make sure you understand this microwave stuff. It's not hard, but please get your sleep. That's the biggest concern. Lack of sleep and a confused mind are the same thing. All right, 10:15 you said, Cole?
Yes.
Okay. Ready? I want to put the Smith chart up here first. And for this one, is it Z0 50?
Z0's 50. 2.5 gigahertz.
What's this?
2.5 gigahertz.
2.5. That's weird, it's usually 2.45. Okay, and for the load?
30 plus J70.
And he wants an L section network to go into this, right? Correct, class? All right, just focus and I think you'll get it. First step is always what?
Normalize.
That's right. We need ZL, which is going to be capital ZL over Z0. In my case, I have 30 over 50, or 30 plus J70 over 50, right? So that's 0.6 plus J1.4. You agree, class? All right, where is that? Well, J1.4 is about right here, if you look. You're going to have to take a look on your own. And the trajectory goes like this, right? And then you got a real part at 0.6. That is about here. And what I'm trying to show you is this 0.6 trajectory is like this. This would be 0.6. So this is going to be this is ZL and it's 0.1. First, can you locate that, everybody? Greg, everybody, got it? Over here, you guys got it? Now, that's outside either, which is perfect. Now, here's what I mean. Look, if we're outside here, I can go to the admittance domain from here, right, if I want, correct? Or if I add impedance, well, I've got, the ZL here is going to be equal to 0.6 plus J of 1.4, right? Now hear me on this. I can subtract J until I get to this point. That's one possible solution, right? That's still going to be in the impedance domain. You all follow me? So I can subtract a certain amount to get to this point. That would be impedance, then I come down. I would, since I'm in the one circle, I take 1 over that, I'd be in the admittance domain, right? And then I'd have to add a positive J in the admittance. That's one possibility. That's actually not the best one. Or what can we do?
You said it's not the best one?
Well, I'm going to show you there are 4 possibilities. Let me just go through. Do you all follow me on that? Or I could subtract until I got to this point right here, right? Now that point down there, that's in the impedance domain, right? And once I got here, I would go to here. And once I came to here, I would go to here, the conjugate point, right? That's one possibility. There are 2, there's going to be a value for this and a value for this. So there's 2 values for the actual impedance we're going to subtract. Since we're subtracting something from that, it means it's a capacitor. Follow me? It's a minus J sense, right? But if I come to this one and I go up here, right? Now I'm going to have an admittance that's going to have a plus J. I mean, it would be 1 plus J something, right? That's admittance. I would need to subtract something, right? That would be a capacitor here. So this one's always going to be a capacitor. If I go to here would be another capacitor. You with me? If I went to here, now remember, that's impedance. That would be a...
If you're in the admittance and you minus J, it's gonna be an inductor.
If you add a plus J to it, no, wait, you
In
want
this
to...
situation, you'll be minus
For,
J.
for which one? This one or this?
Yes, the bottom.
Okay, let's just make up a value. Follow me. All right. Let's assume that this is going to, we're going to subtract a certain amount out of here. We're going to get rid of that. That's going to be a capacitor. You all agree? It's a capacitor. And it's going to be in series. Not a good idea, but you can do it. You can actually do that. So this is going to have a value. I'm just going to say it's 0.5. Oh gosh, what is that value? Let's see. No, it would be actually 0.4 minus J, 0.5. I think that's got a value, real part of 1. I don't remember. But anyway, if we have that, now we go up here, take 1 over that. Now I'm going to have 1 plus J something, right? That's the admittance domain, right? All right, I have to add a negative admittance in parallel, right? Well, an inductor has a positive J impedance, but a negative J admittance. You with me? So you would be adding an inductor in parallel.
Yep.
Yikes. Maybe not the best idea. Y'all follow me in this? So here we have 2 possible solutions. We can go to here, and then add something, or we can go from here, and then add something. Those are 2 possible sections where you have an impedance first, and then an admittance. Y'all with me, class? Or you can do this. And I'm not sure how he says it. There are going to be 4 possible solutions when you're outside. I could start here, but right off the bat, go to the admittance domain. Y'all with me on that? So there's where ZL is. Now I come down here. And if you look at that, that would be YL would be 1 over ZL. Can anybody give that to me? I'm still outside of both. This, you're at the low.
0.26 minus J 0.6.
Y'all hear me? Y'all see this? Now, that's impedance, right? I'm sorry, admittance, right? Y'all with me? Here's the key. See that? We're in the admittance domain. We're going to be adding in parallel, correct? We want to add something. We're out here, say I'm here. I want to add something. I'd be moving along the trajectory point 2, which is pretty big. But I would add it until I hit this point, well, wherever it is, until I hit a value of 0.2 minus J something. Now just follow me. So y'all follow me, class? So it means to me I'm going to be adding, if you look at this, I'm adding a plus J sense admittance. That's a capacitor, right? And it's in parallel. Y'all follow me? That's a preferred way to do it. Now just listen, we're not done here. We can get these values. Does he get these values, all 4 of them, or just a couple of them?
He just does, he does the capacitor in series, then the capacitor in parallel.
No, it should be a capacitor in parallel, inductor in series. But we'll do. You with me, class? Just listen to the thought process. We'll get the values in a second. So now I can land here, right? Now listen. That's admittance, right? If I land here and I go to here, now I got 1 plus j something. Now I would want it to add an impedance, which is a series element that has a minus j sense, right? That would be another capacitor. We don't want a capacitor in series usually. We want an inductor. You with me? So don't just stop here. Keep going until you hit here. We'll do this one, okay? Can you all follow the reasoning? Why? Because 1 over this, right? Remember, we're admittance, right? Admittance here, admittance here. We're gonna, now we go through to here, impedance, 1 minus j something. We add a plus j impedance, it's an inductor in series. That's the one you want. You all with me, class? Please take time to think through this one through. This kind of a problem is likely to show up in a final. So I want you to make sure you can reason through it and know what you're doing. All right, so I'm going to show you the problem we're going to do, and you can help me. I don't know if it's outlined. Does he have, that's the only one he has 2 capacitors in series?
Well, here's the capacitor.
Or I mean parallel series?
Yeah.
That's, it can work in some cases, but preferably you want inductor in series, preferably. All right, so we're going to do it with an inductor in series. I'm going to erase this and redraw it, but we're going to go through my preferred solution. You're going to have to help me. I'm going to start with that load right there. So the next thing I need is YL. Ken, you supplied it, it's 1 over ZL. This would be 0.2. And give that to me again.
0.26 plus j, or minus j 0.6.
All right, now let me draw this, and we're going to do it. That's a terrible circle. That's not too good either. So he has 0.26 minus j 0.6. It's somewhere about here. This is YL. Y'all see this? I mean, actually it's 1 over ZL, but I'm gonna call this 0.1 just because that's where I'm gonna start working for this part, okay? Can you all see it? Now move along the trajectory 0.6, or I'm sorry, 0.26. So that one is something that's going to intersect this circle here and then intersect the circle up here. I want this value on the top one. What is it, Ken or anybody? Y'all realize what I'm doing? To get YL, I got 1 over ZL. This is going to be, if you want me to draw that one. Here's my load. I'm going to put something in parallel, and it will be a capacitor. And the actual value of the capacitor, take a look at the trajectory 0.26. You're probably going to have to estimate where it is. But if you go around, you're going to hit this point, keep going through that point, and then hit this point. Tell me this value. And that's admittance. What is it?
What's that? Well, that's 0.26.
Or Kenan, just tell me this lower point. I'm going to take the conjugate value. Okay. It doesn't matter.
For the top one, I got the imaginary is j 0.44.
Plus J 0.44. And what's the real part? 0.26, right?
Yeah.
You all agree with that, class? So how much did we add? We're down here, and we ended up here, right? So we have to add, that's 0.6 down here, isn't it? Sorry, this is 0.6. So it's 0.6 plus 0.4. So we're adding a total value when we move from here to here. This is going to be a plus j, and it would be 1.04. Is that right, class? Just add 1.04j minus 0.6, and you're going to have a real part of 0.26. You're going to should end up there. Agreed? I'm saying this is the first point. It's actually the second. Because call this 0.1. We actually took 1 over. This is going to be 0.2. Now, that is an admittance. Agreed? A normalized admittance. So we need to add a value of j 1.04, and that's equal to j, and this is the normalized capacitive admittance, right? So that's just j omega c z naught. Do you agree with this? The normalized capacitive impedance is 1 over j omega c z naught. 1 over that's the normalized capacitive admittance. Do you all follow me, guys? So what's the frequency on this? 2.5 gigahertz? Is that right?
Yeah.
All right, so now you know how to calculate omega. What is C going to be? It's 1.04, right? Divided by 2 pi times 2.5 times 10 to the 9th times 50. And what's that value?
1.32 picofarads.
3.2?
1 point.
Now I'm here. Everybody follow? That's admittance. Now we need to go to the impedance limit. Take 1 over that. That's 0.2. This would be 0.3. And the real part better be about 1. Remember, this is Z minus J something.
Wait a second.
Huh?
We're going back into the impedance.
Yeah, we have to. We hit the rim here, right?
Yeah.
Now we got to take 1 over that to get the impedance domain. Y'all with me, class? What is that value? Can
1.68.
anybody confirm that?
That's what I got.
Got it? Got it?
Yeah.
Okay. We're there. Now, if we're there, how much do we have to add to get to there? We have to add plus J 1.6 impedance, right? That means it's an inductor. This is the one I like. I'm just going to tell you, the stuff I'll ask for will require a parallel capacitor, series inductor. I can't be more clear. Good on that? Okay. How do we get the inductance? We want to add J 1.68, right? So it's going to be what? Inductive reactance is J omega L, right? To normalize it, guys,
Over Z0.
divide by Z naught. So what is L? 1.68 times 50 times Z naught over omega, which is 2.5 times 10 to the 9th, right? And that's a bigger inductor. What is that?
5.35 nanometer.
Anybody confirm that? Class?
3. What'd you?
5.35. Yeah.
You all get that?
6, 8 times 50 over 2. Where's the 2 pi?
Is it? Oh, that's a good question. Sorry, 2 pi. Wait a second, no, hold it. Yeah, 2 pi, my bad. What is it? I'm so kidding. My bad, 2 pi.
I had to find the calculation.
Yeah, he had.
What is it though? Is it 5?
what he's 5.34, yeah.
Nah, that's on me, that's on me. Got sloppy. Y'all with me, class? All right, finally, last thing. Now that covers all the bases for the classes of problems. Inside, outside, or outside. Inside the rotated, inside the real, just the article 1, inside the rotated circle, outside both. Finally, the last thing we're going to cover, and I'll speak more about this on Friday, and it will not be on the quiz, but please be attentive so I at least introduce you to it. And this is S parameters. Now, how many have had S parameters in your labs or whatever? Didn't you do measurements with S parameters?
I had an analog.
An analog? Usually they do ABC parameters and H parameters. You probably had HFE, the forward gain and all this stuff, and reverse gain and all that. All of them, ABC parameters, H parameters, S parameters, they're all interchangeable. It's called two-port parameters.
This is something different.
What?
I was thinking S parameters like Bode plots and stuff.
You can do Bode plots
The
for them.
S domain. I was thinking S domain.
Well,
This
no,
is
a little
something
different.
completely different.
So you're gonna have a characteristic impedance here. And then you're gonna have some kind of a network. And this has something they're called the reverse and forward voltage gain and what's called, well, there's different terms for it, but there's actual parameters. This is gonna be port 1. And this is the input side typically. And this is port 2. And this is the output port. This is in your book. And I'm going to assume they're both a characteristic impedance of Z0. Now these represent microwave circuits or transmission lines here. Now there's going to be a signal coming in, and whenever a signal is entering the port, it has a plus sign. So it's going to be assumed there is some V1 plus going into port 1, and there's going to be some V1 minus coming out of port 1. You all with me? These have phase and magnitudes. Can you all follow me on this? Over here, you're going to have some V2 plus going into the port, and you're going to have some V2 minus leaving the port. And now we define the relationship of this with S parameters. So I can say that V1 minus, that's the value of the signal that's propagating away from port 1, will be equal to S11, called reflection coefficient typically, times V1 plus S, and this is going to be 1, 2 times V2 plus. So what happens is I got a signal, plus signal coming this way, a certain amount is reflected, that would have to do with it, V minus. Then I'm going to have a certain amount of signal V2 come in and get back here that's also going to contribute to V1 minus. That's called a reverse voltage gain. You with me? That's the first one. Now for V2 minus, again, that's going to be the signal leaving port 2. It's going to be S21 times V1 plus. That's the forward voltage gain. You can actually talk about this as, this is the forward voltage gain. And this would be the reverse voltage gain. It's going to be that, plus it's going to be S22 times V2 plus. Both S11 and S22 are reflection coefficients. And it should make sense. A ratio of the reflected signal to the incident signal is a reflection coefficient. You all with me, class? Now that's the way they go, and now what happens is, well, how do you go about doing a problem? How much time do I have on your clock?
20 seconds.
Thank you, Kenan. You gave me more than I deserved.
I got 10 seconds on my watch.
Well, obviously you guys are wrong. I got at least 5 minutes.
4.
And here is the final thing. I'm going to give you some problems to do. I want you to read the section for Friday. It's not on the quiz, but please come up to speed. I'm going to cover that, and it will be on the final exam. I'll give you problems and solutions related to it. Now, here's the thing I did want to talk about. I want to be very clear about this. Cole is going to do his demonstration of his project today. Does anybody else have your project ready to demonstrate? You have it? Comes in MATLAB code. Can you just email it to me, the MATLAB code, we'll go up to my office and do it. So that's 2. There's a bunch that haven't done it. Between now and Friday when I leave, it has to be done. So my availability on Thursday, if you want to do it tomorrow, send me an email and I'll respond and I'll set up something. If you want to do it on Friday, I teach from 9:45 to 11 o'clock. Between 11 and 1:15, I'll be happy to do it with you. Y'all hear me now? It has to be turned in Friday, but not when you got to demonstrate your code. Or when the class is over at 2:30 on Friday, which is the last quiz, after I get done collecting the quiz, after that, come up and see me. I want it demonstrated before I leave on Friday. Do y'all hear me? I'm trying to be as clear as I can. If for what?
So we can have it turned in and then just demonstrate it to you.
Yeah, just the code running. All right, just to make sure your code runs, because I'm telling you, I've had some harebrained things. People literally patch stuff in there, it doesn't run. They're hoping to get by with a grade, then they get a D or an F, and why did I get a D or an F on that project? Well, because you didn't do it. Don't do that to me, don't do that to yourselves. Do the right thing, that's what I'm trying to tell you. And always be honest about this stuff, because, boy, it's really desperate to try to lie their way out of it. Now, the last thing I'm going to say is this project sometimes gets stressful if you haven't spent time on it. I would suggest that you take care of this project after this class first priority. Get it done. No matter what it takes, get it done. Because you don't want to be pulling straws Thursday night in desperation. It can cause you to fail. Don't do that. But are you done with yours?
I'm about done.